In this video, we're going to do Newton second, which we are still on. Newton second, but specifically we'll look at position dependent forces. So I've been trying to mention this like a lot of times before in previous videos. If you haven't checked them, check them for velocity, I think, and time and onwards. In position, obviously we have to talk about springs. Springs, you know, there's a spring attached to, and then there's MSM, and here you know that the force that the spring is exerting literally depends on if the square is here, it will be a different force. If the square is here, it will be a different force. As in that if you are compressing a spring at different positions, you'll actually feel different forces. Most obviously when you are maybe compress it too hard, you're expecting that the spring is very stiff or very hard to compress. So springs, we know that they are position dependent, and the other one that I think we need to look at, I think it will be another part type. It will be gravity. We know that gravity is also position dependent also, right? Since gravity is equals to mg, I think. Let me fix. If you want to say, let me say you're talking for projectile. Projectile actually is a constant force, because let me say you throw a ball and it goes up and down. There is always one mg force pulling it down, so it's a constant force for gravity. But we could look at if you look at energies, mgh, it will change as you go up. So for now, let's focus only on the springs. Okay, so for now, I already mentioned that when talking about springs, we know that F net is equals to ma, that's our Newton second, but our total force now is going to be what? It's going to be the spring, of which is kx is equals to mx dot dot, right? That's our acceleration here. This is the reason why the k is negative now is because every time when you're pushing the spring forward, it's always trying to go the other direction. Okay, so let me say this is a spring, this is equilibrium, right? But if I was to get this thing here, it would be trying to push me like this. But if I was to get the box stretched out here, it would be trying to pull me in. So it's always the direction is always opposing the position it is in terms of reference to equilibrium. So here it is in a negative direction, so it's trying to push me away. If it's in a positive direction, it's trying to push me within. So that's why that we have a negative somewhere there. So if we can try to solve this differential equations, because there's a dE, first I think it makes sense to divide by let me leave 0 here, then here I divide it by m both sides, then I'll have x dot dot minus k all over m. I'll go the other way, will be plus x, right? So if we start another course next year, which is called differential equations, a continuation of this course, we will study something called characteristics equation, right? Characteristic equation of this equation is r squared plus omega n squared is equals to 0, and it can be solved by saying plus or minus j. J is a complex. Let me use I because that's what you normally see, depends who's teaching you, right? And then we just know the solution to this equation. We'll see how we go about it in next year, but now we just know that it's going to be c1 cos omega t plus c2 sine omega t. We just happen to know that one of the things that they say they guess in math. Technically, if you do differential equations, you study these equations better, you'll see talking about damping, under damping, there'll be just cool lot of stuff, but hopefully I will also cover it on this course again, or maybe touch it through, if I would say. So also this omega is now worrying you. How did you even come about this omega? Because instead of having k and m, we know that omega is equals to omega is equals to k all over m under a root. That's why here you just see that omega squared I just bring, because I just squared both sides. Then I end up having omega squared is equals to k all over m. So this is just frequency, or natural frequency, and this is measured in radians per second if they're giving you in a problem. What else you need to know? Let me think. Obviously, if you have x of t, you obviously can get v of t, which is velocity, which is going to be negative. You are just differentiating that cos 1 sine, it was cos, is going to be sine omega t plus c2 cos omega t. So now you have your position, now you have your velocity. This is your speed, this one is your position. So this where do you get this? We just guessed it because we know the answer from differential equations, but you get that. You get an equation that looks like this. You try to find that omega will be this, you plug it here, and then maybe using initial value stuff conditions, you can solve for c1 and c2. I don't know what your problem look like, but that's technically what's going on with but it is position dependent. So let me just try to make maybe an easy example. Let me say you are given this is an example. We are given a mass of 1 kg to make it easy for me. Maybe a stiffness k, they call it, another one called Hooke's constant, which you'll see mostly if studying mechanics or mechanical engineering maybe, and maybe initial velocity. I tell you, let me call it v naught is equals to 0, and I tell you that initial displacement is equals to 0.1 meters. Now I'll say compute omega, and omega we know that as k all over m, and then let me just put k9 was m1 under root, and then it becomes 3 radians per second. So we already have omega. Then we can remember our equation for position. It was c1, I think cos omega t plus c2 sine omega t. So you can plug initial values and find. Now I know omega is 3. You can put 3 there, put 3 there. Now make sure that if you're using calculator is in radians, because these are just brought in radians. Most likely in engineering and sciences, radians are the right way to go, right? So we can apply initial value theorem here and solve for c and all that. So let's also think about something here, is that let me draw some sine curves, and maybe cos, I think cos look like this, but I really don't mind what's going on after. I'm interested in the first points. So here at time 0 we know that cos is equals to 1. So at time is equals to 0 we know that cos will give us 1. So that means here we wanted to have x initial. We know that whatever, if we plug in, if we make let me see, yes, if we plug in cos is equals to 0, this will become 1. Remember, once at time 0, and we know that sine at 0 will disappear. So we want such that if we plug in 0, we want this thing to yield out position initial. So already we know that c1 is going to equal to position initial. That's how I thought about it, because at time 0 this guy will disappear, so that means we'll be only relying on this guy, and we also want this guy to, we want cos to be 1, the only way to be, and it's only 1 at 0, or maybe we're interested where it is 0 because it can only be 1 after and periodically throughout. So this guy will become 1, and then that means we force this guy to be initial position. Whatever the coefficient of this will become our initial position, will become position at time 0. So that literally says C1 is equals to x naught, right? Let's look at velocity also. We had a velocity equation. I think we wrote it somewhere in the back. I'm trying to, okay, velocity is at negative c. If I wrote it wrong, remember, if you differentiate, you get something popping in, omega sine omega t plus c2 omega cos omega t, right? So in this case now, let me think. Now we're looking at velocity at time 0. So this guy obviously won't matter for our case, because at time 0 everything with sign will disappear. So we want this term to give us v t naught. We want to give it v initial, right? So that means this guy have to be 1, but this guy will have to give us v naught. That means we'll have to have this c2 will have to be v naught all over omega, so that the omega will help us cancel that one, right? So now we already, by that we already made a conclusion that c2 will have to equals to v naught all over omega. Then with applying initial value theorem, you can just solve the differential equation, as long as you remember what is. Let me write it down again for you. Position is going to equals to c1 cos omega t plus c2 omega t, and then if you differentiate that, you get x dot of velocity in terms of t, or someone want to say x dot of t, which I prefer that also, c1 omega, we get an omega from chain rule inside, sine t plus c2 omega cos omega t. I think here it was supposed to be sine. These are brackets. So as long as you remember these things, and you can apply your initial value theorem, and everything else become history. Thank you. So I won't finish up the example, because I'll also give up more example on the chat for people to work on. Thank you.